Industrial pressure vessels operate under immense stress, containing fluids at thousands of psi. But when you look closely at the bolted flange joints holding that pressure back, the microscopic reality of the interface is surprisingly hostile. Securing a reliable pressure boundary does not rely on a perfectly flat, completely unblemished machine surface. Because absolute perfection at the microscopic level is impossible to manufacture or maintain, engineering a safe seal requires predictably quantifying the imperfections we can accept. This is the ASME PCC-1 standard. It provides the definitive framework for evaluating surface defects. Rather than issuing a single blanket rule for all hardware, the standard lays out a highly specific matrix of tolerances dependent on the mechanical properties of the joint. Every defect tolerance in this matrix is dictated by a single critical binary, whether the system uses a hard-faced gasket or a soft-faced gasket. Soft gaskets are highly compliant, allowing them to fill in and forgive deeper surface defects. Hard gaskets are rigid, requiring a much smoother surface to achieve a seal. Determining if a specific flange will leak requires mapping a defect's radial width against the total width of the flange face. Evaluating a pressure boundary means moving entirely away from subjective visual inspections. It requires applying strict dimensional step functions based entirely on how the gasket material compresses. Before analyzing localized microscratches, the very first step of a flange inspection is establishing the baseline macro flatness of the surface. Looking at figure D21, we start with the T1 measurement. This defines the acceptable variation in circumferential flatness along the seating surface. Inspectors take sweeping dial measurements around the entire circumference of the flange to identify the highest and lowest points. Next, figure D22 details the T2 measurement. This tracks the radial variation moving straight across the surface of the flange face. Checking T2 requires taking measurements along multiple radial lines, spaced every 200 millimeters or less around the full circumference. Table D2-1M shows how the installed gasket material dictates the pass or fail thresholds. Soft gaskets tolerate up to 0.25 millimeters of variation in either the circumferential or radial direction. Hard gaskets restrict this acceptable variation tightly down to a maximum of just 0.15 millimeters. This creates a strict mechanical trade-off. Hard gaskets offer improved assembly with less bolt crosstalk, but their rigidity makes them highly sensitive to any waviness in the flange. These macro flatness checks are the foundational prerequisite. A flange that fails its T1 or T2 limits will not seal reliably under pressure, regardless of how perfectly scratch-free the surface finish appears. Once the overall waviness is validated, the inspection targets localized microsurface damage. The physical threat is clear. A scratch running across a flange face acts as a direct radial bypass for pressurized fluids to escape the system. Evaluating this threat requires comparing two variables, the radial dimension of the defect, RD, and the total width across the flange face, W. The ASME standard mandates that defect depth is exclusively measured from the peak of the surface finish down to the bottom of the gouge. This animated graph illustrates the inverse step function logic applied to these measurements. As a defect's radial width grows, its maximum allowable depth precipitously drops. Table D31M outlines these exact thresholds. The first tier covers short defects spanning less than 1/4 of the total face width. For these small defects, soft gaskets allow up to 1.27 millimeters of depth, while hard gaskets allow 0.76 millimeters. The second threshold covers defects stretching between 1/4 and 1/2 the width of the face. Here, the limits crash down. Hard gaskets are restricted to 0.25 millimeters, and soft gaskets to 0.76 millimeters. Next is the critical danger zone, defects spanning past the halfway mark, taking up to 3/4 of the flange face. In this zone, hard-faced gaskets tolerate absolutely zero defects. Any scratch this wide is an automatic failure. Highly compliant soft gaskets still permit a microscopic 0.13 millimeters of depth here, but the margin is razor thin. The final threshold addresses any defect spanning more than 3/4 of the face width. This is an absolute failure state. No gasket type is allowed to seat on a defect of this width. This matrix proves flange integrity relies on ensuring no scratch becomes deep or long enough to complete a continuous radial leak path to the outside. There is a specialized hardware architecture that completely bypasses these standard raised face assumptions, the ring-type joint, or RTJ. RTJ flanges require a stringent two-stage inspection hierarchy. Crucially, the first stage begins before the joint is even disassembled. Stage 1 is the operational gap check. Inspectors measure the distance between the outer edges of the raised faces while the system is fully assembled. If this gap is less than 1.5 millimeters at any point around the circumference, the joint is compromised. A gap smaller than 1.5 millimeters risks the outer flange faces touching under bolt load. If the faces touch, they absorb the compression, preventing sealing pressure from reaching the internal ring and guaranteeing a leak. Stage 2 is the post-disassembly inspection. Once the joint is open, attention shifts to the interior gasket seating groove. Because RTJs utilize solid metallic rings to seal the pressure, they are rigidly inflexible. Section D4 of the standard explicitly states that all internal RTJ groove damage must be evaluated strictly against the hard-faced gasket defect matrix. That means 0 defects are permitted if their radial dimension exceeds half the width of the groove face. Treating an RTJ like a standard flange by skipping the pre-disassembly gap check leaves inspectors entirely blind to its primary failure mode. Validating a safe pressure boundary is always a continuous logic chain. Flange integrity requires layering macro flatness limits over specific material compression data and mapping those against precise micro defect ratios. ASME PCC-1 provides the strict mathematical boundaries for safe, standardized operation across these variables. But an inspection will inevitably reveal damage that exceeds these quantitative tables. As the introduction to the standard explicitly states, exceeding these limits does not mandate immediate scrapping. It shifts the burden to professional engineering judgment. Engineers must holistically evaluate the specific hardware, factoring in the joint's leakage history, flange flexibility, and the operational risk. Only through this advanced operational analysis can an engineer safely justify continued operation or mandate costly remachining procedures. The standard's matrices calculate the exact mechanics of a leak path, but the engineer's application of that data ultimately secures the pressure boundary.